welcome everyone to the lecture 18 of week 6 of course climate change and extreme events. In the previous lectures we have already talked about return level analysis, we have talked about mitigations, we have talked about adaptation strategies, and we have also talked about risk management adaptations like that, which is very essential when we are talking about climate extremes and we are planning for some sort of mitigation strategies, adaptation strategies like that. In that order, we have to also discuss about what is exactly uncertainty in the climate data set, climate extremes data set, or whatever data we are collecting from, let's say, climate models or some sort of observed data set. So what is the uncertainty associated with that data set? Why it is important? Because when we are using that climate data set for some sort of scenario assessment or risk assessment, it is very essential to know about what is the percentage of uncertainty within that projected outcomes, or what is the value with associated with the error bars, which is very important when we have to look at the decision making or risk assessment of any systems like that. So in this lecture we will primarily talk about what is exactly uncertainty, what are different types of uncertainties, and how we can analyze it. So the learning objective of this particular lecture is definition of uncertainty and its source in climate projections. We will talk about different statistical techniques for quantifying uncertainty. We will also talk about methods to reduce and manage uncertainty in risk assessment, and we will also talk about uncertainty analysis to the real world climate applications as well. So what is exactly uncertainty in climate scenarios or science? So uncertainty is in climate science refers to range of possible outcomes in your climate predictions and projections. Due to it is possible that because of the incomplete knowledge about the system, or it might also possible because of the inherent variability within the climate system itself, which is not able to captured by whatever the model we are using for prediction of that climate variability in the system. So therefore these two types of major incomplete knowledge or inherent lack of inherent variability within the system can originate some sort of errors or uncertainty in the projections or predictions of the outcome, and that can create the uncertainty bounds in our predictions. It is also possible that when we have higher lack of incomplete knowledge and higher inherent variability is not accounted by the model itself, then we have a very higher amount of uncertainty in your model projections. So these kind of the uncertainties can be arise from multiple factors. It could be limitation in the data or model, or it could be because of the understanding of the complex environmental processes which is not completely incorporated in the model framework itself. Therefore it can produce some sort of uncertainty in our system. So it is very important, essential to basically acknowledge or recognize the uncertainty in our system, because it helps us to understand the potential range of future climate scenarios and their associated risk. For example, if we know about what could be the uncertainty in our predictions, we would be able to make a certain informed decision based on the scenario assessment. So majorly this uncertainty can be divided into two parts. One is called aleatory uncertainty, which is also called natural variability, and the second is called asymmetric uncertainty, which is lack of knowledge. So aleatory uncertainty can be because of the intrinsic variability, extrinsic variability, some sort of heterogeneities or diversity or environmental fluctuations, which is primarily driven by inherent nature of the processes, which is not accounted in the model itself, and therefore we have some sort of randomness or random behavior of the system that can create some sort of natural variability, and which is not accounted by the model itself, and therefore we have the prediction is not that exactly the same what we are observing in the real world scenarios. Hypsometric uncertainties are those where we have a data limitation, model structures and parameterization issues. Suppose we are finding the parameter of the model, it is also possible that the model parameters are not exactly the real scenarios are, and therefore it can create some sort of uncertainty in our predictions. Statistical approximation, sometimes we approximate some data into some different types of statistical methods or distributions that might also create some sort of uncertainty in our system. Simplification and assumptions, human biases and dependency on other sources, that is sometimes of creates a lack of knowledge or hypsometric uncertainty in our system. So, primarily measurement error, uncertainty about the variability and process stochasticity are the primary driver of natural variability and the lack of knowledge jointly, which can infer the results of our model predictions, and that can create the uncertainty in our modeling data set, a climate projections data set. So, there are some sources of uncertainty in climate projections. For example, if you are talking about climate model uncertainty, so let us say you are developing some sort of climate model. So, that model has input variables, which can be your multiple different types of input variables, which we are entering into the model, and then we are getting some sort of output variables, and within this framework we have some sort of parameters. Okay. So, then parameter of choice. So, for example, if we are simplified the approximation of the modeling processes, it is might possible that whatever parameter we are choosing, it is not correctly representing the real scenario, or maybe it is oversimplified the processes of the natural world. That can create some sort of uncertainty, or let us say variation in the modeling technique and assumptions. If you are assuming some sort of different techniques or assumption, or missing some sort of processes in the modeling itself, it can also create some sort of uncertainty in the model approach. So, when we are developing a climate model, primarily the parameterizations and the process interpretation or process incorporation in the model setup itself can lead to the model uncertainty in our climate modeling setup. And there is another uncertainty or randomness, or let us say biases in our future emission scenarios. For example, we do not know exactly which path the future process leads to or evolve over time. So, for example, we are talking about different emission scenarios. We do not know exactly which way the future climate change will go, whether it will be higher emission scenario where we have very high emission, and that will basically lead to more GHG emission and more climate extremes across the world, or let us say we have moderated that emission in the future time scale, and therefore we have less amount of GHG emission relatively, and that can basically relatively manage the extreme conditions also. So, therefore, these uncertainty in the emission scenarios can also lead to some sort of error bars in the future projections that primarily depend upon policy decision. What is the role of policy in shaping the emissions? So, which way we are we will move in future, it depends upon what the policy decisions. Technological advancement, whether we are removing those old techniques which is creating some sort of more GHG emission or sort of problems with newer techniques or renewable energy sources, or some sort of those technologies which basically can mitigate the harmful effect caused by GHG emissions, like that. Or energy consumption, or basically impact of energy use on emission scenarios. We can optimize that energy, and we have to work on those sources which is less harmful to the environment or climate. That is basically some sort of emission scenarios. So, therefore, based on multiple pathways, we have to find out which way the future will lead to, or which will evolve, and therefore it will give us more precise understanding about the pathways plus their uncertainties based on different your parameters. For example, policy decision, technological advancement and energy consumption. Some sort of internal variability where the elementary uncertainty can also arise. particularly let us say if you are modeling the climate of a certain region, there is a ENSO effect, or let us say sudden volcanic eruptions, or let us say ocean atmospheric interactions. These are the internal variabilities, or those might create some sort of short term climate fluctuations and can also influence our climate projections as well. So, whatever we are, so these processes might possible that we are not including in a simplified climate models, and therefore the fluctuations caused by these different processes might create short term climate fluctuations, which is not captured by our longer term projections of the climate. So, that is also possible possible source of uncertainties in our climate projections as well. How do we quantify these uncertainty in climate models? So, it is a very simple process. For example, we have to run the simulations, conduct the multiple model simulations to explore the outcomes. Then we have to analyze the results. Analyze the result means examine the simulation data to assess the variability and all. Because we are working with the multiple models at the same time, we have to average the outcomes, calculating the ensemble mean of the data, or with their uncertainty. Let us say you have 10 model or 15 model or 20 models like that. So, in that model you have multiple different outcomes based on their different n models. We can calculate the mean behavior of all the models with their standard deviations, with their errors, and then we can calculate the uncertainties with that. Once we have done this, basically we assess the model performance, evaluate the model accuracy and reliability based on the historical run or historical observations and all, whether our ensemble model framework is completely capturing the historical variability or not long term. Once it is confirmed the historical run or reliability of the model, then we can quantify the uncertainty in the historical period. What is the uncertainty in the model predictions in the historical record or historical time period, like that. Once we are able to quantify, we can also quantify the uncertainty of the individual model as well, and then we can remove those model where the uncertainties are very high, and then we can take only those model which are satisfactorily within the range of the lesser uncertainties of certain modeling frameworks, like that. So, this way we can optimize the uncertainty, we can reduce the uncertainty, and we can rank these models based on their accuracy level and with the lesser uncertainty, so that we can have a better estimate for the historical period. Once we have the better estimate for the historical period, we can basically go for future conditions, and because we have already know about what is the uncertainty in the historical period, you can you can tell about what would be the uncertainty in the future scenario run for these models as well. So, this is some sort of ensemble modeling cycle where you can use the leverage the process interpretation of multiple different models. It is possible that one model is better in sea and atmospheric interaction. There is another model which are better in, let us say, atmospheric and land interaction, or there is another model which are very good in let us say snow and glacier interactions and like that. So, you are integrating all these models together, so that you can have all these process interpretation in one framework, and then you can quantify the uncertainty based on the projections level. So, this is one way of quantifying the uncertainty in the climate models. There is another way which is called Monte Carlo simulation in the climate modeling, where you have to identify the input variables, determine the parameters and condition for the simulations. Then we basically select the random values for each input variable, which is called random sampling of inputs. Then we run the simulations, execute the models with the sampled input data set. Then we basically produce the results with the simulations, generate the climate outcomes, and then we analyze the outcomes, climate outcome of distributions, examine the range and frequency of the outcomes, basically probability and magnitudes, and then we quantify the scenario likelihood, assess the probability of the different climate scenarios, like that, and then provide the overall insight on the uncertainty of our climate model projections. So these are the two ways we can basically quantify the uncertainty in the climate models. Here is the one example which shows that different climate variables, for example 2-meter temperature, temperature maximum, temperature minimum, and wind gust. So this is basically you can see that this is a raw ensemble mean data set, then we have corrected ensemble mean, and then we have observed data set. So if you can see here in the initially the raw the raw and the corrected ensemble mean for like this. So you can see that the raw ensemble mean is completely away from the observed data set, and which shows the higher uncertainty in higher time durations like that. So you can compare your observed data set with the raw ensemble mean with the corrected ensemble mean, and then we can quantify what is our overall accuracy of the corrected ensemble mean modeling compared to the observed data set. Then why it is important to quantify uncertainty? It is also very important to understand, because if you do not know about the uncertainty, let us say you have one value with some certain bounds is basically important, which can use for multiple vulnerability assessment, risk assessment, or hazard level assessment like that. So whenever you are predicting a value, it means there is some errors associated with it because of the lack of knowledge or lack of internal variability which is incorporated in the model setup. Once we incorporate these uncertainty in our model predicted values, we can clearly tell about what is the risk level, what is the vulnerability level, or what is the hazard level of that particular event in a particular locations. So therefore it is very important to have a complete idea about uncertainty in the climate projections or climate modelings. So assessing the probability and consequences of uncertain climate impacts is the important where we need to know about the uncertainty in risk assessment using the uncertainty assessment of our climate models. So for example, probabilistic risk assessment, which helps to quantify the potential risk of different climate scenarios, which can aiding in the identifying high risk events and developing mitigation strategies. It is also very important to understand about the sensitivity analysis, because it identifies which variables or assumptions have the most influence on the model's results. It is also important to have a robust decision making, because if you know about the uncertainty in our prediction, we can have a better decision making framework to focus on finding the solutions that are less sensitive to specific uncertainty or providing the flexibility in the face of unpredictable outcomes. So here if you look at this figure, it tells about the vulnerability in y-axis and in x-axis the range in the hazard estimate. So for example, you have quantified the 10th percentile lower bound, average value, and the 90th percentile. So these are your uncertainty estimate with your average value. Range of the hazard estimate means, let's say if you are talking about any climate extremes, precipitation extremes, temperature extremes, etc., and you are talking about their average values with the climate projections with their 10th and 90th percentile bounds, which are the uncertainty bound. Based on this value, you can compare your system resilience or system vulnerabilities. For example, maximum estimated damage threshold less vulnerable, which means the threshold are very high, it is not going to affect your system very easily, and it is considered to be the less vulnerable compared to the other system. If the vulnerability is little bit higher, then this is average estimate, or if you little bit more higher, for example, then the minimum estimated damage threshold, the damage threshold is very minimum, and therefore system is more vulnerable towards any particular hazard. So if you compare your uncertainty predicted value with your system response, then you would be able to look at the risk associated with the different uncertainty levels. For example, if you talk about this particular region, we can say that there is a maximum estimated risk, because it's a upper bound where the values are very high compared to the average values, and where your minimum estimated damage threshold, which is the system is more vulnerable towards particular hazard level, and therefore it might create more significant damage when we are comparing. So therefore, we have to know about the uncertainty as well as your system vulnerability levels, so that we can have a better understanding about what is the risk associated with the different climatic streams on a particular systems like that. The another use of the uncertainty estimate of climate projection is scenario analysis for uncertainty management. For example, when we are talking about the future time step or future scenarios, we do not know exactly which pathways future will follow, right? Whether it is a low emission scenario, whether it is a higher emission scenario, whether it is a moderate emission scenarios like that. So therefore, in order to understand about which pathways the future will go and what would be the uncertainty of each different pathways, it is basically very important to have understanding about these different pathways as well. So there are two common scenarios. One is called representative concentration pathways, which is called RCPs. RCPs generally are used in CMIP 5 IPCC IPCC reports, where they have done the analysis for historical period, because we know about that, and they have defined multiple emission scenarios, and based on that they have projected the future let's say rise in the temperature or extreme precipitation events or multiple other climate variables, and with their the uncertainty bounds. Uncertainty bounds, how they are defining, because basically they have done the the run of multiple different climate models, and they are integrating together and calculating the uncertainty of each different runs, and they are calculating the overall uncertainty of your projection systems. So therefore, we have multiple RCPs, representative concentration pathways, and we have associated uncertainties. Now we have 10th and 90th percentile bound, and we can compare with the system resilience or vulnerabilities, and then we can assess what is the risk associated with that particular system. For example, the CMIP 6 report of IPCC is using the shared socioeconomic pathways. There they are using the shared socioeconomic. They are little bit amplified or corrected the RCPs. Here they have also incorporated the socioeconomic growth of different region of overall world, and therefore they are calculating the uncertainties associated. Now if you can look at it here, there is more uncertainty compared to the RCPs, because we do not know about exactly which way the future will lead to go, or how much uncertainty will be there. If we have included the socioeconomic growth as well, the uncertainty bound will increase, and therefore we have to compare the 10th and 90th percentile bound in order to get in more clarity about climate vulnerabilities and their the hazard proneness of that different climate variables. So this is one example of Indian case study. Here the map of the India is not correct. It is not the correct boundary of the India. Okay, so so basically here you can look at it. There are multiple regions which is shown: India, Pakistan, South Asia, Nepal, Bhutan, Bangladesh, and Sri Lanka. And they have done some sort of the future changes in the precipitation for six countries as well as the South Asia. So you can look at it. There are multiple projection scenarios, and SSP, let's say 1, 2.6, SSP 2, SSP 5, and they have done some sort of an analysis. So in all these analyses, you can see that there is a dark line which is suggesting the mean behavior of all the projections, with their lighter shades, which are basically say the climate uncertainty associated with that particular bound. So the higher values can be very high, and the lower values of the shade is also lower. So within that range, the temperature or precipitation can vary in any way. That is basically the overall message is. So here when we are talking about the uncertainty of the particular variable, it is we are saying that the value, so when you are calculating the average, which does not mean the value will be exactly same. It can be anywhere within your upper and lower bound with the average value, right? So this is how basically we interpret the climate projections uncertainties. How do we handle these model biases, or let's say structural uncertainty? Let's say if you have run the model for the historical scenario, and the model is incomplete in the sense of process interpretation or process incorporation, or let's say the data limitation is whatever data we have provided or parameterization in the model is not that sufficient, which can lead to some sort of uncertainty. Therefore, in the historical period you would have certain uncertainty in the model, and then how we can basically quantify that uncertainty for that historical period, because in the future we do not know exactly, we do not have any observations. For the historical period we do have observations, therefore we can calibrate our model further so that we can remove the or at least minimize the uncertainty at some level. So that is basically called bias correction or identifying the biases. So for example, bias correction is one technique, which is basically we compare the historical model run with your model projections, and then we can reduce the uncertainty present in the model. We use some sort of quantile mapping approach, and then we adjust the quantiles and remove the uncertainties. Or let's say we can use some sort of iterative adjustment using the model calibrations. You can use the Bayesian inferences or Monte Carlo simulations to basically remove the uncertainty in the models like that. What is exactly model bias? Model bias refers to systematic errors in the predictions model by model, often arising from the incorrect assumption, data limitations, or oversimplified representation of complex systems. These biases can lead to projections that are consistently off in one direction. Sometimes it is too low or sometimes it is too high, affecting the model's accuracy and reliability. The structural uncertainty is basically the uncertainty which arises from imperfect or incomplete models. This occurs because no model can perfectly represent every aspect of a real world scenario or system, and simplification, assumption, or omission in the model can introduce errors. And therefore, to address this structural uncertainty, we have to mitigate ensemble modeling or use of multiple different models with varying assumption in common. So therefore, for example, here if you look at it, this is basically a raw data set, then we have bias corrected, this is the observed data set, and then we have done some sort of bias correction, removing the uncertainty in the model. Now the model is behaving more or less like our observed data set. So that is called, we are removing the model based on our bias correction or error quantification method, and then we are removing the uncertainty within the model so that it can at least behave like what we have already observed in the historical scenario, and that can reduce the uncertainty in the model. For example, here also if you can look at it, the raw is very under prediction. Now we can correct with our model data with the observed data set, and therefore the model has been predicted very closely to that observed data set. So why it is important to have the uncertainty? So far we have already discussed about, there are several methods where you can calculate the uncertainty in the model projections, or you can repeat the model prediction exercise multiple times with different models together to reduce the uncertainty in single model with multiple model incorporations like that. Why it is important to have an uncertainty? So basically, the development of dynamic adaptive policy. For example, we have to describe the current situations of modeling of climate system of one particular location, what is their objectives and all. We have to analyze the problems, vulnerabilities and opportunities using the transient scenarios. Then we have to identify the actions, for example, efficacy or the transient scenarios like that, or maybe we can talk about the vulnerability and the opportunities. Then we have to talk about what is the development of adaptation pathways and map. Based on that pathways, we have to select which pathway is preferred, which pathways we have to follow, and where we have less impact on the climate system. Then we have to determine the contingency and action triggers. We have to find out the plans so that we can minimize the risk. Then we can talk about a dynamic adaptive plan for minimizing the risk, and then we have to implement that plan in a certain region, and then we have to monitor it, whether the plan which we are implementing based on whatever the climate projection we have done with the uncertainty assessment is actually working on the ground or not. And based on that monitoring step, we have to follow up that action so that we can make sure that whatever we have adopted based on a certain locations, it is actually following as per our plan or as per our understanding, as per our lesser impact on the system caused by your climatic streams like that. Therefore, uncertainty estimation is very important to have all this information about what would be the likelihood of the pathways in the future time steps like that. So, this is the one example of flood defense planning with uncertainty rainfall trends. For example, we know about potential rainfall scenarios. Based on that, we can develop the flood defense strategies. We can evaluate the resilience scenarios, so whether it is working or whether it is not working. If it is not working, then we have to revise our strategies. We have to work out alternative flood defense strategies, or we can implement that strategies and then we can ensure whether it is working all right for the future change as well as the historical change as well. Or maybe we can talk about, let us say, adaptive management in the flood defense. We can identify need for flood defenses. Then we can talk about design flexible flood defenses, monitor rainfall patterns, detect new rainfall trends. Then we can talk about trigger or strategy adjustment, and then we can upgrade our or expand our defense system so that we can incorporate all these changes within the system as well. What are the challenges in the uncertainty estimates are primarily three types. Data limitations, we have lesser data, therefore there is a biases in the data, incomplete data like that. There is a communication barriers, complexity or non-experts, we have complex processes or whatever we are modeling, it is we have to incorporate multiple other processes as well. Misinterpretation of metrics, oversimplifications or parameterization can be misinterpretation of metrics like that. Or computational complexity, high resource data set or time constraints can lead to us some sort of uncertainty and challenges, which is why we have some sort of we have to improve our uncertainty analysis so that we can incorporate all these points as well. How do we enhance the model validations? We have to better calibrations, reduces the biases, and then we can accurate uncertainty representative, or maybe we can develop the improving transparency, for example trust building or collaborative or innovations or independent verifications or improved techniques, which can also improve the transparency of our modeling setup so that we can have minimum uncertainty in our model projections. Uncertainty is, so what is the summary of this lecture? Uncertainty is inherent in climate projections, we cannot avoid it will be there, but we can minimize it in climate projections and risk assessments. Quantification methods are there, which can include ensemble modeling or based on some sort of statistical analysis, bias correction, quantile mapping and all, which can basically remove the uncertainty in the historical period, and that can be used for the future steps so that we can have minimum uncertainty in the future scenario assessment as well. Then based on our uncertainty quantification, we can make some sort of effective decision making that requires scenario analysis with uncertainty, and we can compare our results with the adaptive strategies so that we can have better plan, and that can execute in the real world scenarios like that. So this is all about for the today's lecture. In the next lecture, we will talk about the summary of week 6 and one assignment based on we have discussed about risk assessment or return level estimates and their uncertainty quantifications as well. Thank you so much for your attention.